Hello, in this video I'm going to work through a few problems using integral calculus with technology. Our first example here is about this Fresnel function, which is big S defined by the antiderivative or the integral of sine of pi t squared over 2 from 0 to x. And so it first asks us to graph the function, which would be the derivative of the Fresnel function, y equals sine pi x squared over 2 on the interval of 0 to 3. I've done that here. I've also asked Geogebra to find the extremum, which is the troughs and peaks, and also then the roots, because those are going to be significant or important for parts C and D. Use the graph in part A to sketch the graph of S on the interval. Well, we know that this is the antiderivative, and so the antiderivative is the slope of the we know this is the derivative. We know that the derivative is the slope of the actual function. But if I try to graph the integral of this function, then it gets an undefined answer. And so what I can do then is open up Geogebra CAS there, and I get integral of f for the variable x. You can see here we have the letter I, so this is a complex number. And so Geogebra doesn't want us to, or doesn't quite allow us to graph those complex numbers. So I've gone ahead and put this into Wolfram alpha, which does in fact allow us to graph these complex numbers. And we see, let's just trace the derivative. So the derivative at 0, 0 means the slope is 0, which is correct. The derivative y at x equals 1, that means the slope is 1 when x equals 1. And here we can see that the slope is 1, roughly, 1 at x equals 1. And then we have another root, which is going to be 0. So the slope is 0 at 1.41. And we can see that corresponds to this point on the graph. So we can see already that our roots here are equal to the points where the slope equals 0. Right? Our point here at the origin, and then our peak here at 1.41, and then just past 2, which is going to be this point here. When we have a root on the first derivative, that means the slope is 0 on the function. And so at 2, actually, and then 1 up here, just past that at 2.41. Okay, and so that will give us a hint for the relative extrema S on the interval 0 to 3. The extrema are the peaks and troughs. That's these points here, the ups and downs, the peaks and valleys. And again, Wolfram has a calculator that will tell us the exact values here. So on the interval of 0 to 3, we've got 1.41 and 2.4. These two here, these roots 2.45, 1.41. And here it gives us the precise numerical value, and an irrational or a surd there is root 2. So if we want to estimate root 2, what I've done here, we can just say square root of 2, and we get 1.41, and that is in fact this root here. And then we've got root 6, which is obviously not 2, but is in fact 2.45, the next one. Square root of 6. 2.45 here. And so we can see when the slope of the derivative is decreasing, those roots correspond to the peaks on the actual function. And that makes sense because the slope of the if the slope of the derivative is decreasing, that means that the rate at which the function is increasing is decreasing. And so that would correspond to the peaks. So when the slope is decreasing on the derivative, then those roots are the peaks on the function, and then that would mean that when the slope is increasing on the derivative, those roots are the troughs on the function. Those are the low points, right? The slope is increasing, so we've got a negative slope, a less negative slope, a net less negative slope. We've got a 0 here, and then the slope is increasing on the function, which is at 2 or root 4. And then it says 2 root 2 here. Let's say 2 times the square root of 2 gives us 2.83, which is in fact this point. Right? So that's significant, that when the slope is decreasing on the derivative, those roots are the relative maxima or the peaks. When the slope is increasing on the derivative, those roots are the relative minima or the valleys or the troughs. And then the inflection points. The inflection points are going to be where the slope of the derivative changes direction. The slope of the derivative changes direction at the peaks and troughs of that derivative. Right? So we've got 0, 1, 1.73, 2.23, 2.24, 2.65. The peaks and troughs of the derivative are the inflection points on the function. Right? So that's going to be significant for our next example here. Bearing that in mind, we're working with extrema and points of inflection again. Right, so it says the graph of the function f, small f, consists of 3 line segments joining the points here. The function big F is defined by the integral of that function. So we've got a piecewise function. This is the first derivative, so remember the roots of the first derivative are equal to they occur when we have a peak or a trough on the function, and then the minima or the maxima, the peaks and troughs on the derivative, are the inflection points on the function. And so that's going to be important when we go to graph that function. So all I've done here is enter these values into the spreadsheet, and then in order to find the antiderivative here, sketch the graph of f. We've done that. Complete the table. To complete the table, what I did is we're looking for the integral. And so these are very simple integrals. We've got a segment here that has a slope of -1. We have y-intercept of 0. And so the integral clearly is -1/2 x squared, that function there. And this intersects, this corresponds to exactly what we're looking for. We want a peak at the root of our first derivative, and then we want an inflection point at the trough of our first derivative here. So then our next segment from 2 to 6 is given by this function here on the derivative. We've got a slope of 1, and then we've got a y-intercept of -4 if we carry out that line segment. And so we've got a bit of a problem here because we don't have a continuous function. We want this green first part to connect to this purple second part, right? Because we want it to be a continuous function. So remember, we have that constant of integration, c. In order to get a continuous function, which would correspond to our inflection point here at b, then we want to move this point here at 2, -6 up to 2, -2. In order to do that, we need to add 4. We need to add 4. Our constant of integration is 4 there. And so now we see our integral starting to take shape here. And the third part of our integral, we just want to integrate 1/2 x, and then our y-intercept is going to be down at -1. Our integral here is then just the same 1/2 x squared times 1/2, because our slope is 1/2, and then -1x. These are very simple integrals, but once again we have a bit of a problem because we don't have a continuous function here. We've got the third piece of our function way up here. We need it to be down here to be continuous. And so what we need to do is move this point, which is at 6, 3, we need to move that down to 6, -2. In order to do that, we're going to add -5, which is our constant of integration, and then we get our smooth continuous integral there. So in doing that, we can then plot all of our points or complete the table, which I've done over here. Right, and find the extrema f of big F on the interval. So the extrema I here, right, I is where we have a root. Our extrema E or A is where we have a root again. Remember, this is the same phenomena as we found in the previous example. When the first derivative is at root, then we have a trough or a peak on the integral or on the function. And then determine the points of inflection of f. Again, that is the exact same thing as we just worked with a moment ago. And so when we have a trough at the first derivative, that means we have a point of inflection on the function. And so you can see that the slope is increasing in the negative direction, and then it takes a change here and it starts to get to a more gradual negative slope, right? So the point of inflection is where the slope changes from increasing to decreasing, just exactly like the first derivative changes from decreasing to increasing. So the magnitude or the rate of negative slope here is it's getting greater and greater, and then it's getting less and less as we come down to our trough. Right? And is C a point of inflection? No, it is not, because it's not a relative maxima on the first derivative. Is M? Well, this is the end of our function here, and so we don't really know. Maybe then our next point would be over here, in which case M would be a point of inflection. All right, so that one was pretty easy, again, using the very helpful program we have here with Geogebra. And for our third example, we've got a practical problem that you've probably seen in a physics book. We've got velocity and acceleration. A car is traveling in a straight line for 1 hour. Its velocity v in miles per hour at 6-minute intervals shown on the table. These are 0.1 because 6 minutes is 1/10 of 1 hour. So t, we got t measured in hours, and so this is 0.1 hours or 6 minutes. We keep t measured in hours and keep this as a decimal in the tenths because velocity is still measured in miles per hour. All right, so we have the time and the velocity measured out on the table every 6 minutes for 1 hour. Produce a reasonable graph for the velocity v by graphing these points and connecting them with a smooth curve. And so what I've used is I put all these into a spreadsheet on GeoGebra, and then I've used the spline function and the list of points, which is L1 here, and it's given us this nice smooth graph. And so that's not exactly the way the velocity moves, or this is not the exact path or the exact motion, but it is relatively close. And so we've done that. Find the open intervals over which acceleration a is positive. Well, acceleration is positive when the velocity is still increasing, so we've got from point 0, from time 0 until time of 0.4 hours, or 4 times 6 minutes is just 24 minutes. And then the velocity decreases between that point and then point h, which is 7. And then it increases again up to 1 hour. 7 times 6 is 42. So from 42 minutes to 1 hour, for those 18 minutes, the velocity is increasing, as was velocity increasing from 0 to 24 minutes. Velocity was decreasing between 24 and 42 minutes. Find the average acceleration of the car in miles per hour squared over the interval. Well, we have to do a little bit of algebra here. Pretty simple, actually, and if you guys follow along in physics, then you'll know that the average acceleration is equal to delta v over delta t. And so we've got v final minus v initial over t final minus t initial. And we can say this equals 60 miles per hour. And then this is multiplied by 0.4 hours, or 150 miles per hour. Right, and so I found that by saying TF minus TI, right? So TF minus TI, TF is 0.4, TI is 0. And then in that window of time, we go from 0 to 60 miles per hour. So our change in velocity, our delta V change, delta, is 60 miles per hour. So we increase from 0 to 60 miles per hour within 4 units of time, which is actually 24 minutes, 0.4 hours. And so we just divide 60 by 0.4, we get 150, and then we've got miles per hour, and then we got 2 hours on the bottom, so we need to say per hour per hour. So we increased 150 miles per hour within that. So if we kept at that same rate at the end of 1 hour, we would be going 150 miles per hour is basically what that means. All right, find what does the integral of v of t signify. Approximate this integral using the trapezoidal rule with 5 subintervals. Again, we're going to have to do some algebra here, or some calculus, which is really just algebra with some tricks to make it go faster. All right, and so here's our trapezoidal rule. Let f be continuous on the interval ab. The trapezoidal rule for approximating the integral from a to b of f of x dx is approximately b minus a over 2n. N is the number of intervals. And so it said we're using 5 intervals. And so we've got the trapezoidal rule ends up looking like this here. We've got the integral from 0 to 1. 0 to 1 looks like v of t dt is equal to, or approximately equal to, 1 minus 0. Again, this is b minus a. Here's b. Here's a. 1 minus 0 over 10. Because we have 2n, we're taking 5 intervals, 5 subintervals, so 2 times 5 is 10. And then we're going to take that f of x0. F of x0 is 0. We're going to add to that 2 times f of x1, 2 times 10. I'm sorry, if we're doing 5 subintervals, then we're going to go at 0, 2, 4, 6, 8. Because we need to stretch that out over the entire period, the entire interval. So 2 times 20 for that first subinterval, 0.2 and 20 there, and then we're going to add 2 times the second subinterval here, 60, plus 2 times the third subinterval here of 40, plus 2 times the fourth subinterval here of 40, plus, so we've got plus all of those, dot, 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 plus at the end just the last value. So we had the first and last value, plus 2 times the intermediary values. You got 65 there. And so all of this adds up to 385 in parentheses there, 385. 1 minus 0 is 1 over 10, so we got over 10, and that equals 38.5 miles. The integral, or the antiderivative of the velocity, is just the position. And so if we have the function as position, velocity is the change in distance over the change in time. And so if we integrate velocity, then we're just going to end up with the position. Approximate the acceleration at t equals 0.8. Well, we can use Geogebra there. Not that one. This one here, and let's zoom in. We're looking at 0.8. And so we can do this a couple of different ways. It depends how precise we want. So we want to approximate the acceleration at 0.8. Well, I like to zoom in as close as possible, and so I'm going to say that the acceleration, remember if our average acceleration is equal to delta v over delta t, so if we want to get a point approximation, we're going to do basically the same thing. We're going to say a is equal to v, I'm going to say 0.81, that's our starting velocity, minus 0.79, that's our, sorry, this is our starting velocity, that's our ending velocity, and then our change in time is 0.02. And so if we look at that, So 0.79, we're at 39.2. 0.81, we're at 40.8. So we get 40.8 minus 39.2 over 0.02, which equals 80 miles per hour squared. So that's our point acceleration. We could also do this using, we could use 0.8 as our starting point and 0.9 as our ending point. And that'll, what I think that does is gives us the average acceleration between these two time periods over that 6-minute period, which I don't find as accurate, but I think it depends on the method you want to talk about. And so we can take 0.9 and 0.8, 50 and 40 as our starting points if we want to use a different method here. And then we could also say, or we could say A equals, what do we have, 50 and 40? 50 minus 40 over 0.1, or 10 over 0.1, or 100 miles per hour squared. And so you can see there's quite a big difference depending on how close you want to zoom in and what starting and ending point you want to use there. And so when doing your physics homework, it's best to know what your specific physics professor wants you to do as far as methodology, and usually that'll be explained pretty straightforwardly. But as far as math goes, we're just interested in this equation that the final velocity minus the initial velocity over the change in time is going to give us our average velocity over the interval. In this case, we're looking for instantaneous velocity, or that's how I interpreted it, so I wanted to get as close to that point as possible and shrink down our interval so as to not give us an average acceleration over a longer period of time. All right, so that is a little bit of integration with technology. Again, it'll help us to improve our accuracy and reliability and then increase our speed and efficiency in doing these problems, but it is also very important to understand these phenomena that pop up with integrals. To review, the peaks and troughs on the first interval, sorry, on the first derivative, are the points of inflection, where the slope changes from positive to negative, and the roots on the first derivative are the peaks. The roots on the first derivative are the peaks and troughs on the function, and then the points of inflection on the function are the peaks and troughs on the first derivative. And so those are of significance for understanding functions, especially graphing them out. Okay, thank you.